Hey, North Haven Middle School. This video is for algebra, but if you're in pre-algebra and you want to do some simplifying radicals, stay tuned. It's actually some pretty cool stuff, and I know a lot of you in pre-algebra, you guys are really smart. A lot of people that I've either considered for level 3 or put in level 3, or even if I haven't considered you for level 3, there's a lot of smart people out there that it might be worth doing. They're actually kind of fun to figure out. This is something I wish we could be in school to teach. There's a lot of fun we could have with this, built to some props to the tops questions. I might even end with a props to the top question today, so you can move someone's seat at the dinner table. Maybe, I don't know. You can figure that out. But without any further ado, let's get started and get going on this. So there we go. Simplifying radicals. That's what we're going to be working on in this video. These are all radicals. They are not simplified. We're going to talk about how to simplify. In fact, all of these are examples that I kind of plan on going over. Simplifying radicals is useful when you need an absolute exact answer. So it's really useful in physics. And it's going to be helpful with Pythagorean theorem when we do that later on. When you need an exact answer. Here's what I mean by that. Let's just jump right to our first example. So rad 12, square root of 12. All right, so square root of 12 is probably going to be about 3.5, okay, if I'm estimating that in my head, since the square root of 9 is exactly 3, the square root of 16 is exactly 4. This is almost halfway in the middle, so it's probably 3.5 or a little bit less than that. So if I need that number, if I want to write this out as a decimal, I'm going to have to estimate it, because if I wrote out the whole thing, it's going to be a really long decimal. It's going to be an irrational number because it's a non-perfect square. We talked about that already this year. It's going to be a really long decimal. It's never going to repeat in a pattern. It's never going to terminate. It's going to keep going on forever and ever and ever. So what we can do in math is we can simplify this and bigger radicals by kind of breaking them down. So, for instance, let's just realize that, well, the square root of 12 is the same thing. If I just break this up into prime factors, if you remember prime factors from maybe 6th grade or 5th grade, 12 is the same as the square root of 2 times square root of 2 times square root of 3. Okay, because 2 times 2 is 4, 4 times 3 is 12. Now, the reason I break it up like that is because, well, realize what I have here. If I write it like that, look at what you're looking at. This is really going to be, just this part is going to be the square root of 2 squared. And that part is going to be the square root of 3. Well, look at this part in particular. If I have the square root of 2 squared, we talked about this in our exponent chapter. The square root of a square cancels out. They're inverse operations. Square rooting something and squaring something are opposite. So this is just going to be 2. The rad 3, square root of 3, there's nothing I can do with that, so I'm just going to get the square root of 3. But that's going to be my final answer. The square root of 12 you can rewrite as 2 square roots of 3. And again, if you want to simplify it and use this in math, in other physics formulas later on, and in Algebra 2, when you're doing stuff like this, this is going to be really helpful, because remember, the decimal, no matter how many places you write, it's only going to be an approximation. It's never going to be an exact answer. This is exact, and you can use it in equations and formulas. You could also, instead of breaking it down to the prime factors, you could rewrite it as just, well, wait a minute, that's going to be the square root of 4 times the square root of 3. You can jump right to here if you don't want to get the prime factors every time. And if you do that, well, this is helpful because the square root of 4, that is a perfect square. The square root of 4 is exactly 2. And again, square root of 3, I can't break it down anymore. It's not a perfect square. So I just get 2 rad 3. You could just jump right to the answer that way. So that is how you simplify radicals. We're going to be kind of breaking down the numbers in there, pulling out factors. And if we can find perfect square factors, that's going to make this even easier. So let's look at this example. This is kind of a silly example, but it's kind of just going to make my point. For instance, rad of 225. So we just talked about, all right, how can I simplify that? What's that going to come out to be? And you might already be realizing why this is a fishy example, but let's just go to the end. We talked about pulling out perfect squares. Well, obviously 25 is going to go into 225. So if I break this up as the square root of 25 times the square root, how many times does 25 go into this to 225? 25 goes into 104 times, so it's got to go into 208 times. So it's going to be 25 goes into 225 9 times. So this is really the square root of 25 times 9. Well, if I break that up, that's the square root. Let's write that again. The square root of 25, the square root of 9. Square root of 25 is 5. Square root of 9 is 3. So this is 5 times 3. So my answer is just 15. And yeah, 15 times 15 is 225. So you could just known that right away. But I'm just pointing out how you can kind of simplify what's in a radical, what's under a square root to kind of get to an answer. So this one, everything was able to factor it out. We pull out all perfect squares and we're left with just a number. Other times, like when we did the square root of 12 a second ago, and we do that, that might just be an answer of that. So sometimes when you simplify radicals, you're just going to still have a radical in your answer. Other times, if you can do it all out, you could simplify it just to a number. Remember, we're trying to get something exact. We don't want to write a really, really long decimal. So if we get an exact number like 15, awesome. If we write this, well, this is exact. It's 2 times the square root of 3. That is getting kind of an exact answer, not an approximation. All right, let's do one where we got to break it up again, one that will come out with a radical in the answer. So, and this is kind of fun, and the more you do them, the more you're going to recognize certain patterns. You're going to recognize what is a perfect square, what's not a perfect square, and that's going to be really helpful. So here I got the square root of 48. So again, right off the bat, I'm thinking, okay, what perfect square is going to go into there? And you might be thinking, oh yeah, 4 is a perfect square. It's a really useful perfect square, and it goes into it. So 4 times 12 is 48. So I can rewrite that as the square root of 4 and the square root of 12. Square root of 4 is obviously 2. So now I got 2 rad 12. But here's where you got to be careful. This example is going to be a little bit trickier. We know that the square root of 12 can be simplified more. We just did it in the beginning of this video. So we know that the square root of 12 is actually equal to 2 rad 3. We just did it a second ago. And then when I bring down this 2, I'm going to have 2 times rad 3. So this is going to simplify to 4 radical 3. And that's going to be my final answer here. Now, if you're really, really smart and you really, really know your factors really well, I told you pulling out perfect squares is going to be super helpful. The bigger factor you can pull out, kind of like when you're simplifying fractions, the bigger the perfect square you can pull out, the easier your life is going to be. So if you realize right off the bat that, yeah, 4 times 12 is 48, but you know what else? The square root of 16 times the square root of 3 is going to equal the square root of 48. And the square root of 16 is obviously 4. And well, now I get 4 rad 3 a lot easier. So the better you know your times tables, the more work you can save yourself, which is pretty nice. All right, so you're getting the hang of that. It's pretty easy. How can I make it harder? Let's throw in some variables. First, let's do a quick review of what we were doing with some variables before we were on this little extended break. Square root of y to the 6. We're going to simplify radicals like that. Now, this is an easy one because if we rewrite this with a rational exponent, I hope you remember that that's y to the 6th to the 1/2 power. Or really, y to the 6 over 2. I hope that's all coming back to you because that's stuff that would have been on your test last Friday had we had school last Friday. 6 over 2, that just simplifies to y to the 3rd power. And that makes sense that the square root of y to the 6th is going to be y to the 3rd. I could really break this down if I wanted to, if I'm looking at it as simplifying the radicals, which is what we're going to be looking at now moving forward. This could be broken down to the square root of y to the 3rd and the square root of y to the 3rd, because y to the 3rd times y to the 3rd, remember I add my exponents, is y to the 6th. That makes a lot of sense because that's going to be the square roots are going to cancel each other out, and I'm just going to have y to the third. All right, because y to the third times itself is y to the sixth. So that's kind of a review. So now here's the big question. And if we were in school right now, this would be a props to the tops question. So just yell it out if you can figure it out. What's going to happen when I find the radical of something, say, like y to the ninth? And if in your head you're thinking, oh, that's just going to be y to the ninth in parentheses to the 1/2 power, so that's going to be y to the 4.5. Okay, yeah, you're right, but that's not how we're going to write these answers. I don't want to have decimals and fractions as my exponent. I want my exponents to be whole numbers, or in this case, I really want to write it in simplest radical form, so I want my answer to be in radical form. So, how are we going to do that? Think about it. How can we simplify this in radical form? Well, think about, I can break this up a ton of different ways. I could write it as the square root of y to the fourth and the square root of y to the fifth, because 4 plus 5 equals 9. Maybe that's going to be helpful. I could write it as the square root of y to the third and the square root of y to the sixth, because 3 plus 6 is 9. Maybe that's going to be helpful. But the best way of doing it is to pull out the biggest perfect square. We talked about that a problem ago. So really the best way is if I write it as the square root of y to the eighth times the square root of y to the first, because 8 plus 1 is going to be 9. The reason this is the best way is because I pulled out the biggest perfect square. The square root of y to the eighth is just going to be y to the fourth. The square root of y, I can't really do anything with, so it's just going to be rad y, and that's going to be how I want you to write these in simplest radical form. So really, whenever you have an even exponent, you know the square root of that is just going to be half of it. So if you have an odd exponent, just break it up as -1, so 9 minus 1 is 8, y to the eighth. You have your extra y over here in the radical. That's going to stay in the radical. The square root of y to the eighth is just going to be y to the fourth. So that's how we're going to deal with variables when we're simplifying variables under the radical. All right. Some stuff that is kind of an extension of what we were doing before, but also new, is when I have them both together. So if I have the square root of 49 t squared, I really probably could put that on your exponent test, because I can break this up as the square root of 49 and the square root of t squared. I can break it up like that. The square root of 49 is 7. The square root of t squared is t. So that's just going to simplify to 7t. And I'm done. There's no radical left over, and that's okay. I have no fractional exponent. I have no decimal exponent, so I'm good. This was a perfect square. Everything worked out great. Now, when I have a tougher example, let's say here's a non-perfect square, 75, and we'll do y to the 15th. Well, now I should really look at this in two parts. I should look at the coefficient, the 75 as one part, and I should look at my variable as the other part. So let's just look at the square root of 75. So actually, let's break this up so we can actually see those two parts. So the square root of 75 is one part. The square root is y to the 15th as the other part. All right, what perfect square is going to go into 75? I think it's pretty obvious. We can pull out 25. Square root of 25 is going to be exactly 5, and 25 times 3 is 75. So the square root of 25 is exactly 5, so I get 5 rad 3 for this part. How am I going to do y to the 15th? This is an odd exponent, so we're just going to break it up as the square root of y to the 14th and the square root of y. And why are we doing that? Because the square root of y to the 14th, that's the biggest perfect square we can pull out of y to the 15th, because whenever a variable is raised to an even exponent, that's a perfect square. and 14 is the biggest even exponent we can get out of there. I'm going to get y to the 7th, rad y. So here's my answer. I'm just going to clean it up and put it together. I'm going to put the stuff outside the radical together. I'll put the stuff inside the radical together. And my final answer is going to be 5y to the 7th, rad 3y. Like that. All right, and again, if that was a little bit fast, rewind it, pause it, go back and watch it again, and see how we do that. All right, I'm going to do one more last example. All right, this will be the last one I do, and then I'm going to try to look to get you guys some work for how to do these. There's some really, really great websites. I found a really good YouTube video that kind of explains it, goes a little bit more in depth than we have to, but explains the first part that I'm showing you really, really well. And expect to see some assignments soon that are with this, because if we were in school right now, this is what we would be doing. All right, and we're going to be multiplying radicals, dividing radicals, adding and subtracting radicals. Ms. Khan has made some videos to help out with that as well, so be on the lookout for more of those in the coming days and weeks. All right, so this will be the last problem that we do today. I got 60, x to the 3rd, y to the 4th, z. All right, so I have a lot of stuff in there. But again, I'm just going to look at each part kind of on its own. So let's just first look at the rad 60. Are there any perfect squares you can pull out of rad 60? Again, I can break up 60 into 6 times 10. I could break it up into 3 times 20. Those are things you can do. But is there a perfect square in there? 4 times 15 works, and the square root of 4 is a perfect square. So that's going to be the one you're going to want to pull out. There's a way to, if you can't think of 4 times 15 and you can only think of 2 times 30, you can only think of 6 times 10, you can still get to here. I'll show you how to do that in a little bit. So here I'm going to get 2 rad 15 for that part. Looking at the x to the 3rd. Again, it's an odd exponent. So I'm just going to break it up as x squared and x, and the square root of x squared is just x, so this is going to be x rad x. The square root of y to the 4th, it's a square root of an even exponent, so I can just cut it in half. That's just going to be y squared. And the last part, square root of z, well, there's nothing you can do with that. That's just going to be the square root of z. So now I have to put all of this together. You want to put your things outside the radicals together with other things outside the radical. You want to put your parts that are inside the radical together. So my final answer is going to be 2x y squared. And then what's inside the radical? I have 15. I have an x. And I have a z. And that's going to be my final answer. Okay, so that's how you simplify radicals. We'll do this with fractions. We'll do this with multiplication. We'll do this with other problems later on. So that's how you do that. Right now, I'm just going to show you really quickly using the square root of 60 how you could have got to 2 rad 15 even if you didn't think of 4 times 15. This might be helpful, especially when we get to some bigger and tougher radicals. So this is kind of just a quick aside, but it's worth showing, especially if you have a tough time pulling out the perfect squares. So if I had the square root of 60 and I said, okay, let's simplify that radical, and I can't think of 4 times 15, maybe you just think of 6 times 10. Maybe that's the thing you jump to. All right, so if that's the case, well, I'll have the square root of 6 and the square root of 10. All right, there's no perfect squares left in each, but I could still break this down as the square root of 3 times the square root of 2, and break this down as the square root of 5 times the square root of 2. So really, it's kind of breaking it back down into the prime factors like I talked about in the beginning of the video. But notice that I have a square root of 2 here and a square root of 2 here. And the square root of 2 times the square root of 2, or the square root of 2 squared, that's just going to equal 2. So I'm actually going to get, that's going to come together and just be 2. Square root of 3 is just going to be square root of 3. Square root of 5 is just going to be square root of 5. So I'm going to get that. And there's nothing more I can do, but 3 times 5 is 15. So I still get to that 2 rad 15 anyway. If you pull out the perfect squares, it makes life a lot easier. But you got that. You can still get to your answer as long as you know your times tables, as long as you know how to factor, as long as you think you can still get to the final ending answer. All right, so that's how you simplify radicals. We're going to be doing more videos later on, multiplying, dividing. When you divide, you got to be careful because you're not allowed to leave a radical, a square root, in your denominator. So we'll talk about rationalizing the denominator. That'll be good. All right, but this video is already over 20 minutes, so we're going to cut it off there. All right, my dog is going to say goodbye to you. Say goodbye. All right, and we'll see you guys real soon. Stay safe. Wash your hands.